Assalamu alaikum, everyone. Uh, I hope you are fine and doing well. So today I'm going to discuss one of the most important and first modern block cipher. And first of all, let me thank you all for attending my online series of lectures. I'm quite delighted that so many of you could make it today possible. Uh, uh, Last night there was some problem regarding Zoom software. That's why I'm unable to deliver my lecture. I basically delivered my lecture, but unable to like you can say, but there was some problem with my video, so I just don't upload my video series of my third lecture in one of my course, Introduction to Cryptography. So here I come up with another idea, another topic of my course. This is quite important topic since its first data encryption standard is the first non-linear block cipher officially approved by basically NIST, National Institute of Standard Technology in 1973. That the proposal was from IBM, and then this was approved by NIST in 1975, and then uh, basically federal processing unit basically approve it and make it as a standard officially standard encryption mechanism that can be utilized in banking as well as in other online services. So what I would like to present to you today is DES. Today, my topic is of quite interesting to those who revised my previous lecture, in which I have devised some basics of modern block ciphers, which consist of P box, S box, and their different characteristics. Like it may be straight, it may be uh, compressible, it may be expensible, means to say it may be one to one, it may be one to many, it may be many to one. So, in order to classify all these P as well as S boxes, and there are some standard component in modern block cipher, like splitting of binaries, and then combining the binaries, and then swapping, shifting. These are all basic component of modern block ciphers. If you can remember, in my last class, I have discussed some standard transformation of the AES. It's sub-byte transformation, shift row, mixed column, and add round key. Fundamentally, the modern block cipher consists of substitution, permutation, and third component is node is, which is quite useful, is uh, add round key. Means to say for each round we have a sub keys that is basically based on your initial key. At the time of encryption, you have very large key. Then on base of the large key, you have sub keys for each round. We have device sub keys. What does it mean? For each round, we have perform multiple substitution as well as multiple permutations. Uh, but basically, these the component in modern block ciphers basically it's more or less generally based on two type of mathematical transformation. One is linear transformation, another one is non-linear transformation. The thing which you must realize in this in today's lecture is that nonlinear component of block cipher, which is your substitution box, that basically diffuse your whole all over the encryption or digital information. For that, but it has some lack of while you devise encryption algorithm that use only substitution, it has some drawbacks. But as compared to if you utilize only linear component, which we call it permutations, in mathematically we can say it is as just say symmetric groups. Um, uh, let us start with some. Our goal today is to uh, understand DES, which is Data Encryption Standard, in a best possible way. I have divided my lecture into five main parts. First, I will discuss some historical background of data encryption standard and to define then some basic structures of DES, how DES work, how Feistel cipher is utilized in each round, and then we'll discuss some building block and building elements of DES to describe the round key generation process and then analyze some drawbacks of DES. But students, since these DES is consists of 64 bits, I just give you the overview in this lecture. But in order to realize this data encryption standard in an actual way, so you have to run this program of this data encryption standard to over some softwares. It might be Python, it might be MATLAB implementation. So in order to realize what does actually DES mean and how DES is fundamentally run. For me right now here, I will just discuss some component of DES, how DES is working, and what are the weaknesses. Dear student, let me tell you one thing, that DES is fundamentally failed due to its weak key structures and semi-weak keys. Semi-weak keys means to say you can retrieve some part of ciphertext with by using by if you use the weak keys or semi-weak keys, then if which is it may be passive, it may be active attacker, they can recover some part of your ciphertext. And uh, let me go to next slide with some objectives of our today class. So, dear students, these are some objectives. As I discussed earlier in my previous discussion, I give you the larger view of my today class. Um, uh, Let us start with data encryption standard is symmetric key encryption that is published by NIST Institute of National Institute of Standard and Technology. Historically, this was proposal was given by IBA in 1973. The proposal request is devised by NIST, and then in March 1975, the draft of is approved by registered by federal in 1975, and the draft of the federal information and use this as a draft of federal information processing standard. And this is fundamentally utilized in number of digital banking system at that time in 1975. Um, but after the some drawbacks of DES, it was replaced in 2001 by AES. So these are some block diagrams. Let me tell you why. So these are some block diagrams, and if you can say see this one, These are some. Okay, this is a basic diagram, data encryption block cipher diagram. Here you can see the basic component of block component is 64-bit plain text. It takes 64-bit plain text, and then this 64 plain text is divided into chunks that passes through the mechanism of DES and 56-bit key. DES is consists of key length of DES is 64-bit, but we have to omit some parity bits from that fundamental key, which is of 64-bit, and there are 8 parity bits. We omit these 8 parity bits, and we will get 56 bits key. Then from 56 bit, we have omit another chunks of 8 bits, and we will get 48 bits for each round. We have basically different number of keys for which is consists of 48 bits. So through substitution, basically expansion or shift operation, which are fundamental component of block ciphers, uh, are utilized in order to reduce 56 bit into a 48 bits key, that basically uh, make it compatible. Our whitener with me whitener, I whenever I utilize the word whitener, I means to say XOR. So that is why XOR is compatible. You can apply XOR only if you the number of bit length is same between two elements, then you can XOR them. If number of length in any bit stream is not same, then you cannot perform XORing in that case. So these are more or less encryption and decryption mechanism of DES. What actually DES, what is actually going on in this black box of DES? So in order to understand what is inside the DES, basically the structures of DES. So let us go further in order to understand the basically this black box of DES. So the encryption procedure is made of two permutation, which we call initial and final permutation. Or sometime in some books, basically authors write as final permutation as an inverse permutation, and it has 16 rounds. So each round we cannot achieve a very good encryption characteristics with just one node. So the modern block cipher use number of rounds in order to achieve the good algebraic as well as statistical characteristics of any block cipher. Whenever I mean to say algebraic characteristics, then more or less I mean to say I am discussing about substitution boxes, which have very strong cryptographic characteristics, like it must be highly nonlinear. It must satisfy avalanche and strict avalanche criteria. It must satisfy bit independent criteria. It must have strong combating capability in case of a linear attack as well as in case of differential attack. So in the statistical analysis, I mean to say we have some data stream, and we have applied this modern block cipher to some encryption algorithm, and in order to satisfy some statistical analysis. So our encryption medium means to say encrypted image must satisfy some statistical analysis, which is uh, flatness or uniformity of histogram, and then chi-square distribution, goodness of chi-square, and then entropy, which is measurement of randomness in your data sets, and then MSC, PSNR. MSC is basically based on discrete metric and discrete metrics of distance between original and encrypted image, and it must be high. And moreover, we have another metric based statistical characteristics, which is PSNR, peak signal to noise ratio. And then we have, in case of signal, we calculate SNR, signal to noise ratio. And then we have some statistical differential attacks like NPCR, number of pixel rate, change rate, and then USC, unify, I call it unify average pixel change intensity. So these are some statistical analysis that our constructed. If you have constructed any block cipher, it must satisfy these characteristics. It's not just the algebraic characteristics. It must satisfy some statistical characteristics too. So, dear student, let us come up with another type of discussion, like general structure of DES. Basically, this is the black box of DES. As I told you in my previous lecture, this is a black box. What is actually going on inside this black box? So this is something that is going on inside the black box of DES. Like, it take 64 bit and apply initial permutation, then 16 number of rounds, and then final permutation or inverse permutation in order to get your basically ciphertext. Here you can see this one. This is 64-bit ciphertext. As I told you, here we have initially 64-bit key length of 64-bit, but for each key we have 48 bits key. So in that first round, we have to apply some Feistel cipher or Lucifer cipher in first round. And Lucifer, the input from this basically block have 48 bits. So I must have 48 bits key for this round. So with the while removing parity from 64-bit key length, I have 56-bit key, and then I use some compression P box that convert 56-bit into 48 bits. And then from these 48 bits, I have applied some shifting operator to generate 16 possible keys, which are basically the keys for each round. Um, Students, we have um, go in into the next slide. Uh, Let me revise it for you. Uh, if I remember my last lecture, let us go back to what I said before in my previous online lectures. Since DES consists of P box, S box, and number of rounds, so P box is basically, let us discuss this each and every component separately. What does initial permutation means? What is inside the first round? What is inside the second round? What is inside this 16 round? And then what does final permutation means, and how we can generate these basically key, and I call it this key generator. So students, I just come up with the initial and final permutation. Here you can see initial permutation is consist of basically it take 64 bits. These let me clarify one thing. These are not just 1 to 64 element. These are basically the I just put in this is over here. Basically, this is these are the 64-bit plain text. So first bit is map on 40th, and then second bit is map on 8th bit, and then so on. 58-bit is map on first bit, and then 64-bit is map on 25-bit. So in that case, we basically shuffle our initial permutation by initial data with the help of initial permutation. In that case, we just transform our 64 bits into another 64 bit. So apply 16 round, then after 16 round, we have say 64 bits. Then we apply final permutation, means to say first uh, bit is map on 40th. Here you can see we just invert the initial permutation. Here the 58 is map on first, then first is map on 58, then 8 second is map on 8, then 8 is map on second bit. And similarly here you can see this one 64 is map on 25, then in that case 25 is map on 64. And if you can see this one, the 58 is map on first, then first is map on 58. In that case we can say these are all just inverse of each other. Basically initial permutation we just shuffle the position of bits. In final or inverse permutation, as I told you, in some standard books we call them as inverse permutation, but in some cases in some research articles or in some books they are use it as a final permutation. So these are again I must say in that case we have straight p box, and in that case in case of final permutation we have also straight p box. So dear student, this p box is basically from if I can realize this as a transformation, then p1 is a transformation from z to 64 to z to 64, means to say it must be a tuple of 64 our binary binary to 64 tuple of 64 tuple our binary, means to say it is a vector space from z to 64 to z to 64. Similarly in the final permutation is also a vector space from z to 64 to z to 64. So it more or less we can say these are just a element of you can say this is basically the element we take from symmetric group of 64 elements. Here, the whole discussion, which is described in Figure 3, is listed in form of 8 by 8 table. So you can see this is a 8 by 8 table. The initial permutation, this is the initial permutation. This is a final permutation. Here, first 58 is map on first position, and 50 is map on second position, and here you can see this is a 25th position. 25th position is map on 64. If I can go back in my last slide, then here you can see this one, the 24 positions, 64 is map on 25. It means this in here 25th position is map on 64, and 26th position is map on 56, 27 is map on 48, and 28 is map on 40, and then 29 is map on 32. and 30 is map on 24, and then 31 is map over 16, and 32 is map over 8. In that case, 64 7 is map on, in that case we can say the 64th position is map on 7. So similarly, in the inverse permutation, we just reword this table in permutation wise. That is, 64 is 25 is map on 64, then 64th position is map on 25, and the basically the first we can say this first is map on for 40, and in that case one can say, and the second position is map on let me give you one example, please wait. So this is the final permutation. This is just a inversion of initial permutation. You can see, if you want to see this, then you can draw just three element initial permutation, then revert them as inverse, as we have discussed in last lecture. So you can get final or inverse permutations. So let us come up with some very fundamental examples to perform initial permutation or permutation box when your input is given in hexadecimal. It will be very good if you can transform this input into a 64-bit element, 64-bit element, and then perform your final permutation. That first is map on 40, and first position is map on 40, second position is map on 8, third position is map on 48 in term of bits. So in that case, you can easily understand what does this mean. Why I have used a hexadecimal, because just to squeeze the input. Otherwise, it's quite not good to write 64 bits, very large stream of bits. In order to understand this one, you have to take just uh, 8 bits, and corresponding to 8 bit, we have permutation p box, or having 8 elements p box. So here we have 64 bits key stream. So for that we have 8 by 8 initial final permutation or inverse p box. So you can take it as a homework, and please verify this. We can get this. First, transform this from hex to binary, and then apply this permutation like this one in table one. This final or inverse permutation, and then you can get its corresponding binary, and then convert binary into hex, whether you get this one or not. Please take it as a homework, and I will ask from you people how you have devised this. And similarly, you can perform example number 2, which is again in the form of hex. It might be quite easy for you people to use final as well as initial permutation in order to understand what does initial and final permutation means. This is once again the example. So, if you can apply the initial, if you have this initial data, and you perform basically the output or the final permutation, this one, when the input is given in this one, so you have to apply the inverse permutations of initial and final permutation to this element, and you will get back the original one. That one, this one is the original one. So dear student, let me sum up this first section of my lecture with that. We have a device or understand the what is actually going on inside the black box of DES. Black box of DSI always means to say the journal diagram which we have discussed in figure 1. of slide number 5. So in black box we have further say we have initial as well as final permutations. So we start with initial permutation, and after that we have some rounds. Inside these rounds we have Feistel cipher. Then we have apply Feistel cipher from one round, two round, third round, fifth round, and then after 16 round, after that we have apply final permutations and get our ciphertext. So what how your 16 round inside each and every round, what is actually going on. So whenever I talking about inside the round, what is actually going on? This is the one of the block diagram that tell us what is actually going on inside your round. And this is nothing. It is just a this whole is as a Feistel cipher. So in each round we use Feistel cipher. So what does Feistel cipher did with some bit stream or initial data? It divide the initial data into two blocks. That is split these into two blocks of leftmost block and rightmost block, and each consists of 32 bits. So then these 32 bits are passes through mixer swapper. What does it mean? The function f is basically concatenate key and 32 bit, and before it has 32 bits, but our key is of 48 bits. What we have to do, so here we have to increase the number of bits in order to apply some function on left rightmost block and number of key. So for that, we have here used expansion function or expansion permutation that basically map 32 bits data to 48 bits. For that, we have applied over here some functions, and that inside the function we have some permutations, shifting, and then in that basically transform your again 48 bits. We have here 48 bits. Then this when we apply function to these, we get 32 bits in order to XOR this 32 bits leftmost bit to the output of this basically box, which is again function of rightmost key and rightmost bits and uh, key of the ith row. So then we have swap basically the output with the right and right with left, and then we join them, and we'll get another 64 bit from this first round. And these basically we repeatedly apply these types of basically swapping, mixing till 16th round of data encryption standard, and after 16 round we get our fundamental ciphertext. So, what does function in that case? This one, what does this block means? Let us explain this block in our slide number 14. How it take 32 bits and utilize some expansion p box and make it 48 bits, then XOR with the key. As I told you, the key for first round, second round is consist of 48 bits, and then we start with 32 bits, and for in the while applying a function f of r rightmost bit and ki means to key of ith round. So we start with 32 bits. So mathematically, we have to end up with 32 bits in order to preserve the clear law of binarization or clear law of bits. So let me explain this with the help of another diagram. What does function that f of r comma ki means? So, dear student, the heart of ds function, we call it this as a ds function. The ds function apply a 48 bits key to rightmost 32 bits to produce 32-bit output. Let us come up with some explanation how we take 32-bit as an input, then some expansion p box. I mean to say, whenever we are talking about expansion, expansion p box is nothing. It is just a mapping from one to many. Basically, input is lesser. In input we have lesser number of bits, and output will produce more number of bits as compared to input. So in that case, our p box will be a expansion p box, and these are not invertible. So here you can see it's a very tricky calculation inside DES. Actually, we don't use completely field or completely, you can say, the invertible structures. But even then, when we perform inverse transformation, means to say decryption, we get back our plain text. It's a beauty of number of rounds and number of shift. If you change little bit in this inside the black box of DES, you will unable to get your plain text back by using decryption algorithm. Also, each and everything is quite devised in a quite expert manner. So let us come up with this to explain this idea of DES functions. So after passing the 32 bits from P box, we have 48 bits. Then we apply Widener. I mean to say uh, XORing the 48 bits with 48 first round 48 bits, we get 48 bits. Then I think about I have end up with 32 bits. I have 48 bits. How I can do this? For that, in DES we have some 8 substitution boxes, and each basically substitution box basically takes 6 bits and map on basically 4 bits. Basically, it's many to one substitution boxes. So this is a if I take it as a transformation, though S1 is a transformation from Z26 to Z24, and this is again the transformation from Z26 to Z24, and then so on. The eighth substitution box is also a transformation from Z26 to Z24. For in that case, if you divide this 48 into 8 chunks of 6 bits, so each chunk is consist of 6 bits, and we pass the each of the 6 bits from each of these 8 boxes. So every basically every substitution box takes 6 bits and map on 4 bits. So if you can multiply 4 with 8, then you will surely get 32 bits, and then apply some straight P box that convert again 32 bits into 32 bits. As I told you, straight bar P box means to say it's a bijective P box. So I end up with 32 bits in the S function, which is fundamentally heart of the S. So in last step, straight P box. So I have to how sorry. Let us explain this expansion P box separately. What does it mean? So here you can see students who have 32 bits, and we have to make it 48 bits. So here you can see this a chunk of 4 bits. This is again a chunk of 4 bits, and this is again these are basically 8 bits of chunks of 4 bits, 8 bits of 4 bit, sorry, 8 chunks of 4 bits. So every you can see the first I take this as a first the 32 bits bit, the first bit I take it as it is, and then 4 is map on 4, and then I take first bit of second chunks map on the last bits of first chunks of expansion, then last one is map on first one of the second chunk. In that case you can see the four bits of 4 block is map on bits of 6 blocks. In that case, 32 bits is map on 48 bits. Here you can see we have 1, 2, 3, 4, 5, 6, 7, 8. 8 chunks of 4 bits. Here we can see by after applying the expansion p box, basically that map lesser number of bit into a more number of bits. That is, we have 32 bits input and we map 32 bit into a 48 bit output. So in that case, each and every when we pass 4 bits from expansion permutation, it give us uh, basically 6 bit, and then again 4 bits pass from expansion p box, so you get 6 bits. And same is the case with 8th block of this chunks. We pass it through basically p box, and we'll get 6 bits. In as a whole we have 48 bits. So, dear student, the P expansion P box is the given in term of tabulated value in table 6. You can realize this as we have realized initial and permutation P boxes. So, Whitener, I means to say XOR after the expansion. DS use XOR operation on expanded right section and round key. Note that both right section and the key are 48 bits in length. Also note that the round key is also only in round key is used only in this step. So let us introduce the idea of substitution boxes. Dear student, in this cases we have basically 8 substitution boxes, and 8 substitution boxes are basically transformation from 0 to 6 to 0 to 4. And these, if I can say, these are just vector spaces from 6 tuple to 4 tuple. And in that case, if I can generalize the idea, so in that case the matrix of transformation will be 4 plus 6, that in that case. So our each and every after expansion, we discuss how our substitution boxes work in DES. The substitution do real mixing confusion. So DS uses 8 as boxes with E with a 6-bit input and 4-bit output. See the figure 7. So here you can see 1, 2, 3, 4, 5, 6. 6 as input, and we get after passing 6 bit from substitution box, we get 4 bits. In each of the case, we have 6 input and we get 4 output. So in that case, you can see the student here 6 into 8, we have 48 bits, and corresponding output will be 4, 4, 4, and 4 into 8, we have 32-bit output. So these are one of the basically we place substitution box as a rule in figure 8, which to take 6 bit as an input, and first and last bit basically tell you about the row of your substitution box, and the center bits basically second, third, fourth, and fifth bit basically tell you the column of the your substitution box. Here you can see from this first and sixth bit tell you about row, and this tell you about column. So here you can see from this row to this column we get this element as a element of substitution box that replaces 6 bit to 4 bit. So we get 4 bits from after passing 6 bit through substitution box. So we get 4 bits out as an output. So, say we have one rectangular substitution box which is given in table 3. So, it take basically 6 bits and map the 6 bit into 4 bits. When I say it map 6 bit into 4 bits, it means to say I have a transformation from Galva field 2 raised power 6 to 2 raised power 4. Or I can say it's a transformation from Z to 6 to Z to 4. Inside I can say inside of this first row, the element must be from 0 to 15, but it should not be arranged in a ascending or descending order. Each and every row should not be assigned in a some patternized data. It should not be. Otherwise, it doesn't follow the good characteristics, good cryptographic characteristics. And if you don't use a very strong substitution box, you will lose the credibility of your block ciphers. Basically, the confusion capability is lost. If you lost the confusion capability, it is possible that you can recover your basically cipher text or crack your block cipher by the use of uh, linear or weak Boolean functions. And whenever I am saying substitution boxes is nothing. It is just Boolean functions, and these Boolean functions may be good Boolean, maybe weak Boolean function that depend upon certain characteristics, or I can say certain cryptographic characteristics of your data or your functions. And these are balancedness, completeness, bijectivity, strict avalanche criteria. These must be satisfied while you construct a very good substitution box, or while you construct a very good modern block cipher. Without the very strong confusion component, you can compromise your construction or your designing of your modern block ciphers. So, students, right now, substitution boxes can be created in numerous different ways which are available in literatures. So, I must focus on my lectures that I have to follow some basic notation of here. I don't put a very laborious and very complicated algebra, but you just focus on if you learn about some like standard Boolean function, which I have given you the idea in my first some classes where we have developed 16 possible Boolean function on two input binary basically table. We have possibly 16 possible Boolean function. I mean to say we have 16 possible gates, logic gates. So in that case, I have to follow the very simple transformation that take 6 bit and map on 4 bits. So my each and every row in this case, you left this first and first column and first row because I just use indices to just indicate from whenever I say the first row, my rows started from this 14 to 7, then 0 to 8, and then 4 to 0, then 15 to 13, and each and every element in this first, second, third, and fourth row is consists basically the element from Galvafy GF2 raised power 4. So I just converted 0 into a binary, which is 0 0 1 0 1 and 2 1 0, then 3 1 1. Similarly, these are elements 0 to 15. So these are basically it consists of 4 bits. So 0 has 4 bit, 1 have transformed from decimal to binary. It has double zero zero one, then 2 is 0010, then 15 is triple one one. So so let us come up with how to realize this substitution box, how it works. Let me give you some examples, or let me give you some demonstration in example in my next slide, uh, 21st slide. So how it work, let me give you some so you have to utilize the table number 3. So you must have an input as a 6 bit. So I take in example number 3 input or to substitution box. First substitution box is 1 0 0 0 1 1. So dear student, the first row and so first bit and last bit will tell you about the position of row, and the rest of the 4 bits basically tell you the position of column. The output will be given as follows. Here you can see this one. Uh, Let me give you the example. If you can see this one, 1 1 0 0 1. So if you can realize this, the first row, first bit and last bit in 1 1. So the ultimately the if you can see this one, 1 1, this tell you row, and 0 0 1 tell you about column. So here you can see double one, this is the row, and 0 0 1, this is the column. So our output that is generated through substitution was given in table 3 will be 12. Say here you can see this will be result is 12, and then you convert the binary 12 from decimal to binary, you will get 1 1 0. So one the 0 0 0 1 1 yield the output 1 1 0 0. Dear student, so this is one of the application of substitution boxes, how your data is squeezed from 6 bit to 4 bit. So you can take example 4 as a homework, and please do solve it, and it will be a very good if you can take some other substitutions, like if you take 7 bits and tell me what is the corresponding substitution box, and 7 bits is mapped on 4 bits, how you can construct this. And I also urge to say that you have to construct different input and create different corresponding different substitution boxes. If you want to insert some input, say you have m input and you want n input. So after taking this lecture, you must be expert to devise your own substitution box, your own way, how many input you are want to insert into your substitution box, and how many output you want from that function, I mean to say substitution box. So for that, you have to be very much careful, and you must be expert in that. But keep one thing in your mind, that randomly selected any array is not always a substitution box. For that, you have to be very much careful about selecting any array. It must be cryptographically strong and secure. I means to say cryptographically strong and secure means to say it must have some good cryptographic characteristics. So you take this as a homework and so straight P box. Straight P box, I means to say when this is a straight P box that is utilized in inside the black box of DES. Basically, this straight P box or permutation table basically map 32-bit on 32-bit. Um, uh, 2 bits, and here you can see each and every element is basically this is basically 32 bits. It has first row is eight element. The second row consists of again eight element, and third and fourth rows again consists of eight element. So we have eight cross four table, and basically in this case you can see over here 32 bits maps on 32 bits. So in this case, it will be a very good if to have to understand this, you have to take a very small, say four. Instead of taking this permutation p pairs, you have to take some one-dimensional array and sort it, swap it, and then calculate its corresponding output. As we have discussed this in our last previous lecture number two, which is uploaded on YouTube channel of my introduction to cryptography course. So dear students, it's very good if you can pass 4 bits of take 4 bits and take one permutation of 2 by 2. I take it as a 1 3 2 4, and you can pass your like bits 0 1 0 1. So I am giving you the task that 0 1 0 you take input as a 0 1 0 1, and permutation as 1 3 2 4. It is 2 by 2 permutation, and you have to tell me how this permutation is performed on your input line 0 1 0 1. So let me give you another idea that how your cipher and reverse cipher is utilized in DES as well as in AES. So we have discussed a lot about data encryption standard. So let us look into some other matters as we have already discussed. P box, expansion box, substitution box that are utilized in DES. So we have to throw some light over key generation of substitution boxes. So plainly, if I can talk about key, initially we have a 64-bit key length. Then we just drop some parity of 8 bits. We have 56 bits key. For this 56-bit key is then converted into 48 bits key, with each and every round have 48 bits key. For key generation, we have to use some compression p box, basically that if you convert 56, how one can convert 56 bit 56 bit to 48 bits. For that we have some shifting operation as well as some compression p box that ultimately device in order to convert 56 bits to 48 bits and create some round keys for each and every round. For shifting, I must say, if I can talk about shifting, so in a shift, we must say for first round, second, and ninth and 16th round, we have to shift a right shift in a clockwise shift. We have 1 bit shift in every sub keys, and then on other like third round, and third, fourth, fifth, seventh, eighth round we have two shift in our bit stream, and similarly in 10th, 11th, 12th, 13, 14, and 15 we have two shift. Only who have one shift in while constructing the bit key in round first round, second round, ninth, and 16th round. So, dear student, you should not be worried about all these calculation. I will give you the very simple example at the end of this lecture, how you can realize all these situation. What does f means, what does rounds means, how one can generate keys for each and every round, how one can perform final permutations. So for me, if I can add up, these all the algorithm is can be applied on some in order to realize or understand this, you have to be um, not very good, but you have to be a little bit. You must have some little bit expertise in, say, MATLAB, Mathematica, and Maple. So I must say, if you haven't the experienced expert in MATLAB, even then you can realize the actual situation. Even then, you can construct your very good block ciphers. But for you, you have to be basically learn various and different things, and taste different things in your life, as well as in your academics. So for that, really make you some different. Means to say, I mainly say this: you have to be very good in some computational capabilities. Means to say, either it may be any software. So in order to perform, in order to gauge your any model block cipher, for you, you can take some very good lectures on MATLAB is available on Coursera. So I must focus on my lecture, which so the block diagram, the major and full diagram of DES is given in figure 4, that take basically 64-bit, then apply initial permutation, then left and right bit are converted into 64-bit is converted to the leftmost and rightmost block of 32-bit each, and then apply F, and it's F is nothing, it is a DES function. We have, as I told you in my last slides, if you can see the slide number, let me tell you, slide number, say, slide number 13, then you can realize the DES function. Slide number 13 or slide number 14, then you can realize what does F means. And in this, basically the first round, this is a whole about Feistel cipher. In second, we have applied the same thing that we have received from first round. So in that case, we apply the same thing. Or in last round, after the last round, we have applied final permutation, which we sometimes call it inverse permutation in a reverse. For decryption, we have applied the whole procedure in a reverse way. We start with the initial permutation of these cipher text, put cipher text in initial permutation, and perform all step in a reverse order, and finally we perform final permutation and get back our plain text. Uh, so these are some. So how one can generate, the student, how one can generate number of keys and for each round. So initially we have, as I told you, we have 64-bit key. We drop parity and we have 56-bit key like this one. Second, in that case, we have 8 bits parity. We have dropout 8 bits, or you can simply say say I have 60, don't confuse with parity, or don't confuse with how, what are the parities, don't be confused. Or so just take 64-bit key, and then drop out 8 bits. So in that case, we have 56-bit key, that 56-bit key, and 56 is then divided into two blocks, then 28 bits, and then 28 bits. Then apply left shift. Then from this we have applied left shift. In the first round, we apply just one shift towards left. We have discussed the basic component of block cipher, left shift or right shift. It may be, if I can say left shift, I means to say it is a anti-clockwise. If I apply right shift, it means to say I'm going to shift my bits from in a clockwise. So I have applied one P box on this after shifting 28 bits, and compressible P box. Compressible P box means to say I take 56 bits and convert it to 48 bits. That 48 bits basically give you the key length of your first round. So in the same way, we have performed the same operation, same thing. We generate 16 sub keys, and these are the key generation mechanism of our data encryption standard. So these are something we have discussed, and these after dropping the parity table, we have this table of compressible p-box, and these are compressible p-box basically has 56 element, and for how we can perform the shifting as we have discussed over here. In first, second, ninth, and 16, we have just applied one shift, and in here, first there will be no change. In second, there will be no change. In third, we have applied two shift on our bit stream. Then fourth and fifth, sixth, and so on. And 16, we have just only one shift. So key compression table. This is key compression that take basically 56 bit and convert 56 bit into a 48 bits. 48 bits, 50, 56 element, and 56 element are then converted to 48 element. It is quite clear from this table that it is compressible p-box. These are some, you have to verify this with one of the MATLAB simulation code, which I will share with you in my next discussion, and if I can share with you on my WhatsApp group. So, dear student, these are just left and right, and we have 16 rounds. So, after 16 rounds, we have cipher and apply the inverse permutation. So, inverse procedure with decryption, we have get our plain text. So in that case, we can see over here, this is our plain text after applying final permutation. These are our keys, and these are our left and right most block in that is utilized in as a L naught, R naught, L1, R1. That is L 14, L 14, R14. This is L15, and this is a L. Sorry, R15. So this for each round we have a key. If you can, these data is given in term of hexadecimal. You have to convert this into a binary. If you can convert them into a binary, so you will get 48 bits key for each round. Some critics and some uh, desirable or some non-desirable characteristics of data encryption standard. So, dear student, this data encryption standard have fundamentally numerous weaknesses, and the fundamental weaknesses come from short length of key, and it is possible to you can apply all possible keys in order to get your plain text from cipher text, or it is possible that existing computational capability can solve the all possible way, that is 2 power 64 in case of DES. But if you have a uh, generalize the DS from 64-bit to 128, then in that case, it has some strong encryption qualities as compared to 64-bit key length of key, as well as plain text length of 64-bit. I must say, it should not be like that. You just when you increase the plain text length 128 bits, ultimately inside the black box of DES, each and everything will be changed. If I can say, if I have extended the DES from 64-bit to 128 bits, the first thing which I always think about is what will be my substitution box. In that case, my substitution box is taking basically uh, 48 bits and map on 32 bits. In case of 128 bits, my substitution boxes take 96 bits and that map onto some say. In that case, our substitution boxes will be double as compared to standard data encryption standard. In standard data encryption standard, we have used only 8 substitution boxes in order to produce say in order to produce 32 bits after passing through 40 after passing 48 bits from substitution box of 8 substitution boxes, we get 32 bits. In case of 128 bits key length, so or 128 bits plain text, we have 96 bits uh, that have to pass through substitution box in order to get you can say 8 plus 8 16, and then 92 and 96 minus 32, that will give you basically uh, 74. Basically it give you say sorry it give you 64 as an output. Here the number of substitution boxes will be doubled. In DES, we can say we utilize only 8 hash boxes in uh, while increasing the plain length of plain text to 128. So you have to basically convert 96-bit to 64-bit. It means the input corresponding to each substitution boxes will be 6-bit, and that 6-bit passes through S1. It will give you 4 bits. In the same case, we have 16 bits. So, sorry, 16 substitution boxes, and 16 substitution boxes. You have 64 bits that has to be passed through 16 substitution boxes. So each and every pair of 6 bit, if you can divide 64 by 6, say 64 by 6, no, I must say, if you can divide, let me do it, 64, then you have to be 96, and then so you have 64-bit key length, and you have to pass all these convert this into a finalize it. It has 72, then divided by 6, then So 96 is passes through like 96 bit in case of as in our DS standard DS we have 48 bits that has to be passes through substitution boxes and that add up that 48 bits is map on 32 bits. In case of generalizing the idea of DS on 128 bits. So we have DS student 128 bits and we have mm, um, 16 new substitution boxes. And if you can see, 16 means to say 16 and 16 new substitution boxes and that has some 96 bit have to have passes through 16 substitution boxes and then 16 is multiplied by 4 so 4 it means 64 into 6 24 and 4 and then 64 so I'm sorry dear student I'm saying that when you have generalize the idea of 64-bit to 128-bit. In that case, your DES have more secure as compared to 64-bit because in that case, 2 raised power you have to apply 2 raised power 128 possibilities for in order to recover your key, which is not possible by utilizing the computational capability available today in an advanced era. But it might be possible in the era of quantum computing. So, quantum computing should not be mixed up with quantum mechanics. Is quite different. So, we will in some other lecture we will discuss about quantum what does quantum computing and what does quantum mechanics means. So left it right now. So we have if we had generalized the idea of DES to 128 bits, in that case we have all possibilities to recover keys 2 raised power 120s, which is quite high as compared to standard DS. In that case, we have to use the 16 different substitution boxes that take 96 bit as an input and map 96 bit to 64 bit. That reduces the number of bits, and again, each and every substitution box is basically consist of that take 6 bit and generate 4 bit output. So in that case, we can one of the way we can basically reduce the weaknesses in DES. So, dear student, it's quite interesting phenomena that how one can say the we achieve the avalanche effects in our encryption mechanisms. So, while devising this encryption mechanism, let me tell you something that suppose you would like to design a robust block cipher, how would you go about it? Imagine you had constructed a block cipher, and what will be the first step to authenticate the strength of your encryption mechanism? First, give you so let me first give you a brief overview, some benchmark criteria of good block ciphers. A good block cipher must satisfy avalanche completeness, and nonlinear component must be that is substitution boxes must have a good cryptographic characteristics like it must satisfy avalanche as well as strict avalanche, and moreover it must satisfy completeness characteristics and means to say it must be bijective, and moreover the avalanche criteria, I means to say, if you change one bit in a plane or one bit in a key, the resultant will be changed at least 50% change in the cipher text, or at least there will be 50 to more than 50 at least there will be a 50% change in your output. Say if you use some two input binary functions like 0011 and 0101, then if you can use XOR as a binary operation, then your input will be 0110. In that case, that there will be a 50% change while you are applying XOR. In that case, the probability of 0 is zero point 0.5 and probability of 1 is also zero point 0.5. In that case, and moreover, the XOR is the balanced Boolean function. And balanced Boolean function is a one in which input and output are the number of input, the number of zeros and number of ones are same. In that case, we can say a balancedness is one of the characteristics that must satisfy the Boolean functions inside your substitution boxes. So let me elaborate this with the help of example number 7. To check the avalanche effect in DS, let us encrypt two plain blobs that differ only in one bit and observe differences in the number of bits in each. Let us say you have this key, and the plain text is 00, so you will get ciphertext, and the key is remains same, and you just change your plain text with the last one bit key. So in that case, you will get different cipher. Means to say you just change one bit and you will get a completely different cipher. It means to say it satisfy your basically basically, if you can see that satisfy your avalanche criteria. Avalanche can also be achieved. You can, if you can don't change your plain text. If you change one bit in key and to recover it, one bit change key, recover your plain text, you will unable to recover your plain text from ciphertext with just one bit key change in your encryption key. So it's quite informative property, and it's quite good effect on your modern block cipher. And while discussing anything related to modern block cipher, you must keep this property in your mind that while devising any encryption algorithm, it must have some good cryptographic and avalanche criteria. Completeness effect means that each bit of plain text need to be depend on many bit on plain text. That means to say completeness is more or less related with depend upon many bits. It means that the bits of cipher is not just depend upon one thing. It must depend upon more than one thing in order to achieve the good completeness characteristics. So while devising a very good block cipher, it must have some good criteria. Like S boxes, the design provide confusion and diffusion of the bit from each round to each to next round. P-box, they provide diffusion of the bits and number of round, that is the DS uses 16 different round of Feistel cipher. The ciphertext is thoroughly a random function of plain text and ciphertext. Dear students, the weaknesses in S boxes and weaknesses in P boxes ultimately generate the weaknesses in your basic block, which I call it as a uh, black box of DES. So while selecting a S box and P box and key, it must have some group cryptographic characteristics. Otherwise, it is possible that you can compromise your design block ciphers. So, in order not to compromise on your block ciphers, or not to compromise on your what you call a crypto system, you must always while constructing or while taking any substitution or p boxes in your block cipher, it must have some good cryptographic characteristics. And before going into another weakness in DES discussion about weaknesses. Also, weaknesses in key, it really generates some quite uh, good phenomena, but it is not good with respect to cryptography, because if you select a weak key, say I'm taking one example in slide number 39, where I show you how a weak key basically ruin, basically destroy your whole block ciphers. Through wiki, you can basically, when a trade in number of round, then you can, after some fixed number of round, you can get back your plain text. It's quite not very good with respect to cryptographic processes, and with respect to cryptographic demand, that you get your plain text even you are performing encryption, and you get plain text. So in order to get rid from these kind of phenomena in block cipher, we have to take strong key, and we we have to take like apply the key with having some larger length as compared to 64. Why actually all these are happening? It is due to short length of your key in DS. That's why this kind of things are happen in while constructing a short key key length based encryption mechanisms. So it may depend upon which type of basically digital mechanism you are going to use, and which types of calculation you want to achieve, and which types of media you are using. Right now, there are several types of encryption mechanism. It might be for business purposes. It might be a military grid encryption algorithm. It might be utilized for some corporate corporate organization, like your banking systems, where you need more speed as compared to some cryptographic secure cryptography. Yes, they are secure, but here you need in a nano microsecond you have to authenticate your transactions of your money from one place to another place. For that, you should not use the very heavy encryption algorithm in order to halt your system. Like in today, in the era of lightweight encryption algorithm, which are utilized in IoT's Internet of Things. So you have control your number of digital mechanism from remote station, like your AC and your home security can be managed through some remote station, remote area. Remotely, you can access all these things. For that, you have to be very smart, and you have to develop very smart encryption algorithm instead of very high mechanism that halt or that basically halt your low or constrained environment devices. The IoTs in IoTs we have device constrained environment devices that don't have such a high saving capability and having some very high memory allocation and means to say in a simple term high memory like your Android and there are a number of other devices that are included into IoTs. So, dear student, I have discussed a lot. So, let me give you some what happen if you select some weak keys. Um, Let me tell you. Sorry. If you try this first wiki in table 18 to encrypt a block two times, like this is your one of the key which I take select and then we call it wiki. If you just take this plain text and with this encryption we have performed, we get ciphertext. And again, I take this. This is our first round, and then second round I take this as a plain text and pass through the standard DSA encryption algorithm with same key. I get this as a plain text and I get ciphertext. Here you can see the ciphertext in second. This is not plain text. This is ciphertext. I don't apply a decryption algorithm. I'm still in encrypting the thing. So I get back my ciphertext, and this is due to why I have select weak key. So there's always a concept of weak keys. So dear student, I have discussed the this figure in and to apply double encryption, we can get it from sorry, double encryption and decryption with a weak key. We will get back our ciphertext. Dear student, I am now approaching the end of my lecture. Well, I would like to highlight one of the key issue, that is DES structure has some weaknesses due to which I uh, due to which it doesn't sustain a standard. That is why it doesn't remain as a standard encryption algorithm, and this was replaced by AES in 2001. So let us in order to understand this algorithm, I just place one finest example and simplest example with the help of take instead of 64-bit, I just take 12 bits as a plain text and then 12 bits as a 12-bit key. Let me like this one. So the key has 9 bits, and each key ki for the ith round of encryption is obtained by using 8 bits. So if you can realize the actual DS, it has a 64-bit key length, and then we drop some parity, we get uh, 56 bits. Then we apply some shifting or scaling and some expansion p box, we get 48 bits. So in that case we have initially 12 bits, and then we have dropped some parity bits, means to say 3 bits, we get 9 bits key. Then the student, we have, say for example, we have 9 bits key, then we have apply some shifting of dropping one key from this original key, which is of 9 bits. So we ultimately get 8 bits key. So applying here, you can see I just take these one, two, three, four, five, six, seven, eight. So I just take this one, and just I have take K1, then in K2 I apply two clockwise shift. I get K2, and K3 I just apply two times. Here you can see. Um, uh, I just apply, let me tell you, just apply to shift. In that case, if I can apply one shift, I place this one, then no, sorry. In that case, I have applied this anti-clockwise shift, and I put in K1 I have 1 0 0 1 1 1. Then I apply another shift in K3. Then these will be these two bits will be placed at the end of this key. Then I get 1 0 0 0 1 1 and then 1 1. So in that case, I get K3, and then in K10 I have applied all shifting, and then I get K10 because I would like to apply 10 rounds in that case. For understanding, I just take 2 rounds in order to give you some better understanding of DES, how your DES is actually working on. So algorithm, the block of 12 bits is written in the form of L naught R naught, where basically we have to convert 12 bits into 6-bit, two blocks of 6-bit, and leftmost 6 bits are L naught and rightmost are R naught. So the ith round of the algorithm transform an input Li minus 1 Ri minus 1 to output Li Ri using an 8-bit key derived from K. K is a standard key which is of 9 bits. So this one of the I call it Feistel algorithm that take Li Ri and pass Ri with F, that is in standard F of R I minus 1 comma Ki, that passes and XOR it uh, with Li, and then I'll get Ri once again. And then I can say this, I replace Ri with Li, and replace Ri with Li, basically shifting Ri with Li in each round. The output for the ith round is found as follow. Li is Ri minus 1. So you can see this. Li is equal to Ri minus 1. And then one can say Ri is equivalent to like this one. Ri is equivalent to Li, like Li XOR f of Ri minus 1 comma Ki, then I will get Ri. इसको एक बार फिर समझ लें. Ri बराबर होगा Li XOR, यानी जो यहाँ से जो ऊपर से ये जो कैलकुलेशंस आ रही हैं ये वाली, basically Ri is combined by these functions. In that case, f is the function of Ri minus 1 comma Ki, that is XOR with Li minus 1, then this is equivalent to Ri. Here you can see I just put it in the form of some notation, in the form of expression. So I have to perform all these calculations in our simplified data encryption standard. So this is again the DES function for simplified. DES function is applied on Ri minus 1. It expand your Ri minus 1, then XOR with Ki. Then from here you can see this Ki is of 8 bits. So we have just divide from after this step, we divide 8 bits with 4 bits and 4 bit. Then 4 bit is passes through first substitution box and second, and 4 bits are also possible into second substitution box, and we can catenate or join these. Basically from here we get 3 bits, and the output of S1 is 3 bit and output of S2 is also 3 bit. We can join them, we'll get again 6 bits, and which is saved in FRI minus 1 comma KI. So, dear student, what we did here expansion. In this case, we have 6 bits and our key is of 8 bits. In that case, we have to apply this output of Ri. There we can apply some expansion that basically add some 2 extra bits into Ri, because Ri is of a 6 bit, the expansion converts 6 bits into 8 bits in order to perform XOR operation with KI. KI means to say a key for each row. So here you can see 1, 2, 3, 4, 5, 6, and 6 are mapped on 8 bits. These are 6 bits. These are not just, I just put indices. These are not just 1, 2, 3, 4. These are just 6 bits. And you can see first bit is mapped on first, second bit is mapped on second, and then fourth bit is mapped on third, and then third is mapped on fourth, then fourth is, sorry, fourth is map over 4, then third is map over this one is 6, and then fifth bit is map on 7, then sixth bit of the input is map on 8. So in that case, if you can put 6 bit in expansion function, you will get 8 bits as an output. So I have discussed more or less all about this 48 number slide. So let me give you one example how your 4 bits of input is basically mapped on 3 bits while passing through substitution box. First substitution box like this one, and second substitution box. Like you have, like you can see this one from here, you have 8 bits, so you have 4 bits as a combinedly you have uh, 8 bits, and you have to convert this 8 bits into two chunks of 4 bits. So dear student, here you can see this one, these are 8 bits, and you have converted them into a two chunks of 4 bits. So first 4 bits are inputted to S1, and the remaining 4 bits are input to S2. So let me give you some demonstration how it will work. So your basically our substitution box take 4 bits and map on basically uh, 3 bits. So I mean to say my row will, there will be 2 rows and 8 columns, and 8 columns are basically is of start from 0 to 7. This is 0 to 1, and if I can convert them into a binary, one is in 3 binaries, because 0 to 7 consists of 3 binaries. So 0 means 0 3 times 0, and 1 means 001. In that case 7 means 3 times 1. So the first basically element will tell you about row number, and the rest of the 3 element tell you about column. So if you can put these 4 input into S1, so the first element will tell you about the row, and the rest of the 3 binary will tell you about column. So the first row 101 column. For that you have output will be uh, 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 double one one. So in that case, there's a double one one. So same is the case if you can put your these output like 0010 to S2, you will get again map 4 bit into 3 bits. So I have discussed this earlier. So the student, I have no. Let us to end up this lecture. I have to solve, as I told you in my some in my during my class, at the start of my class, I will give you some very brief examples in order to realize that you people have to have realized what actually going on inside the black box of DES. Basically, what is the internal structures of DES with the help of one of the very simple example. You cannot solve the DES, actual DES, which is of 64-bit with hand. Let me give you one very simplified example through which you can easily understand what is actually going on in DES. Let me take one 12 bits plain text and 9 bits key. So I just divide this 12 bits into two blocks of 6 bit, that is L naught and R naught. So key one is of 8 bits. I just drop one bit and I can take one K1 for that is key for first round. So what a expansion function did with R naught, this kind of things I have discussed in my lecture in the, here in this slide 47. Um, what expansion function did? It basically maps 6 bit on 8 bits. Basically, why we have to do it? Basically, our key for first round is of 8 bits, and so our number of bits in leftmost block R naught is of 6 bit. We have either we have to make K1 map on 8 bits to 6 bit, or either we have to apply some expansion function on R naught that map 6 bit into 8 bits. So we have applied this expansion function from this R naught, that is one is map on one, that is this one. First bit is map on first bit, second bit is map on second place, and then the fourth bit, what this is fourth bit is map on third position, then third position bit is map on fourth, then I must say fifth is map on fifth. Then one can say this one, let me clarify. The fourth is map on fifth. Then it should not mix up with the from here. This is one, two, three, four. You can place your binary over here. That is 1, 1, 0, 1. So in that case, these are just a number and you can place it over here. These are number from 1, 2, 3, 4. I just put these number over here, but actually if I place indices, the index from 1 to 8. So in that case, our expansion function map 6 bit into 8 bits, and we XOR expansion function with K1, we'll get again 8 bits. So we divide these 8 bits into chunks of 4 bits and pass each chunks of 4 bits through S1. If we have passed is 0, 0, 0, and then 1, 0, 1, 0 through our S box, that's 3. 4 bits is map on basically 3 bits. If you can see this substitution box, say 0, first row 0, and then 0, 0, 0 column, you will get 1 double 0. In that case, you can see over here, sorry, they just take some different substitution boxes. So that is why sorry, in that case, sorry, substitution box, first substitution box 0, triple 0. So our output will be 1, 0, 1. So here you can see this one, S1 is passes through and we'll get it. Similarly, S2, apply S2 on 1, 0, 1, 0, you'll get 1, 0, 0. So F is basically concatenation of these two input of 3 bits, and this is again an input of 3 bits. So when concatenate means to say join them, combine them, this will get uh, 6 bit, and in 6 bit further we have to apply XOR this with L naught, we'll get again 6 bit, and Li means to say Ri minus 1. If I can put L1, I will get R naught, and R naught is nothing like this one, and R1 is equivalent to R1 L naught XOR F R naught comma K naught K1. So in that case, our K1 will be equivalent to this one. We place L naught is XOR with F of R naught comma K1. In that case, we get L1 and R1, and then we apply swapping like this one. In this case, in second round, we perform the same step, and after applying the same step, we just swap the position. Like swapping means to say left right input is on left side and left input is on right side. In that case, we get R2 and L2. So for decryption, we will perform the reverse operation and given in slide number 54 and 55. Here you can see we get back our plain text is of 12 bits. With the help of this very simplified example, one can say DES is one of the block ciphers that consists of P box, substitution box, expansion function. It may be a expansion function is of type P box, which is a expansible P box, and then some mm, compression P box that take larger input and map on lesser number of input output. So dear student, there are some recommended readings for you. You have to take it very serious and go through from these some recommended readings. And at the end, I must say, and I before I stop, let me go over the key point of my lecture. We have discussed the S, its internal component, its weaknesses, and demonstrate this algorithm with one of the simplest example. Well, student, in this basically this bring me to the end of my lecture. I would suggest we can modify DS by placing some strong confusion and diffusion component based on different mechanisms such as DNA or RNA sequences. Also by adding elliptic and hyperelliptic curves as a key generation mechanism of DES. Till then, Allah Hafiz, and please keeps be at your home, and may Allah bless you all. Allah Hafiz and good evening.